So how we're going to go about solving each of these is we're going to, like I mentioned already, we're going to define the variables in words. So what is X going to represent? What is Y going to represent? That is always a good place to start. Then it can kind of help us piece together the equations. And that's the hardest part here is getting the equations. Once we get equations, then we're just using substitution or elimination. So the algebra part shouldn't be any different than what we were doing last week, but it's getting those equations that's a little bit tricky. So after defining variables, that's when we'll work to find our equations, use one of the solving methods, then state your solution with the appropriate labels. Because we're actually working with applications here, our solution isn't a point of intersection, right? It's not where the lines intersect. Instead, it's going to be completely related to what we're trying to solve here. Okay, so number one, and this is an old assignment, so I don't know that any of this information is all that accurate, but it says last season, 2 running backs on the Broncos football team rushed for a combined total of 1,550 yards. One rushed for 4 times as many yards as the other. How many yards were rushed by each player? So when we're defining variables, that comes from just simply what are we trying to solve for? Okay, what are we trying to answer? We're trying to answer the number of yards rushed by each player. So we're going to let X equal and Y equal exactly that. Okay, the number of yards, so the yards by running back number 1, since we don't have names. And then Y would be the yards by running back number 2. So we're looking for the specific number of yards that each running back ran. So these are fairly short, but another thing that we can do is kind of underline the pieces that might help us build the rest of the equations. So the other one is that they combine for a total of 1,550 yards. So we need one equation for this. And then our other equation is this last sentence where one of the running backs rushed for 4 times as many as the other. So this is our second equation. So for the first one, we need to add up the total number of yards by each running back and get to that total. Well, right now we don't know those specific amounts. Instead, they're represented by variables. So if we take X plus Y, that needs to equal 1,550 yards. And once I've written that part, I might cross it off in a sentence, just making sure that I've actually accounted for that part of the information which shows up in our equation. Then it says one rushed for 4 times as many yards as the other. Does it specify which one rushed for 4 times as many than the other? No, so it doesn't matter which one we'd let rush for 4 times as much as the other. So let's just say 4 times the number of yards that running back 1 ran for equals the number of yards that Y had. Okay, well, now that we have our equations, the words don't matter. Right now, we're just simply solving this. And this is, again, kind of like our warm-up. You want to decide what's going to be best. When we have Y by itself, so I can go ahead and sub Y into the other equation and solve from here. So X plus 4X equals 1,550. So 5X equals 1,550. And thus X equals 1,550 divided by 5, 310. Now that we know X, we can find Y by plugging that back into the other equation. So 4 times 310 equals the number of yards that running back 2 ran for, which is 1,240. So answering the problem, that's the last part. Just state your solution with appropriate labels. We would say that one running back ran for 310 yards. The other ran for 1,240 yards. Okay, so just a quick sentence describing what our solution represents. All right, so you have two others that again start with the variables and equations. There is an answer key posted for this. It's already in Schoology, but I'm going to always encourage you to try your best to build those equations before you even ask me, before you even check. Okay, so even when we get to work time today, at least have a guess to what you think your variable should represent, and at least have a guess to what the equation should look like too. Then you can call me over and say, hey, come check these. But unless you actually have something written down, I'm not going to just come give it to you. Okay, we just simply need practice with all of these. All right, we'll go ahead and flip the page. Because based on, again, just the application, the setup of the equations might be slightly different. All right, so it said Dennis mowed his next door neighbor's lawn for a handful of dimes and nickels. 80 coins in all. Upon completing the job, he counted out the coins and it came out to $6.60. How many of each coin did he earn? Okay, so again, when we're defining variables, it just comes from whatever we're trying to answer. What are we solving? We're trying to figure out how many dimes and nickels he had. So X can be the number of nickels. I'm not going to spell that right. And luckily, it's written down on there, because I wouldn't have spelled it right. And Y is number of dimes. Okay, so defining variables, just again, directly related to what we're solving for. Now, again, I'm going to go through and underline the pieces that are indicating some kind of equation. So one being the 80 coins in all. So this is one equation. And then upon complete earn. So this is our second equation. So something related to the actual value of each type of coin as well. So if we know that we add up the number of nickels and dimes, that's the total of coins that Dennis earned. So X plus Y is 80. So that's not much different than what we had just seen. And then the money is, again, just how does he get to that $6.60 by counting up all the nickels and dimes, including the value of each. So our equation is not going to look much different than what we just had. We're just going to tag on, again, the value of a nickel and the value of a dime. Remember that a dime and a nickel, those are not full-on dollar amounts, right? So nickels would be 0.5 or 05 cents. So 0.05 times X plus how much a dime is worth, which is 0.1Y, and that totals to 660. So we have some decimals in here. That's absolutely okay. And honestly, I think this is a system where substitution or elimination might make sense. With X and Y being on the same side, might be quicker to do elimination. So let's go ahead and do elimination here. But again, I think you can make an argument that substitution could work too. So I don't really like these decimals, so I'm going to try to eliminate one of those. And I'm going to do that by multiplying the bottom equation. I'm thinking 0.1 times what will get me to a 1y. If you don't know, you can always just kind of guess. So 0.1 times, it should be 10, gets us to 1. So I'm going to multiply the entire bottom equation by negative 10, getting me that negative 1y. That'll then allow it to eliminate. So this gives me 0.05 times negative 10 is negative 0.5. And then that's X. And then minus 1Y. And then it equals 660 times 10 is $66, negative 66. And we're going to add that to the top equation, which again, I just copied over. Okay, so it didn't change the top equation at all. This is what allows us to eliminate the y's. Then I have 1x minus 0.5 leaving us with negative point, or not negative, that's positive. How about positive 0.5x? And then 88 minus 66 is 22. 80. Good catch. So how about 14? And then now to get x by itself, we just have to divide by 0.5. That essentially should double it, making x 28. So we have 28 nickels. And in this case, to find y, it's going to be much easier to plug it back into the top equation, where I don't have to deal with any of those decimals. But again, it doesn't matter at all. I'm just going to plug it into the top one and say 28 plus y equals 80. And thus y equals 80 minus 26, which is 54. So Dennis earned 28 nickels and 54 dimes. You're right. I did 26, 52. It's a good reminder of why we should be using pencil when we do math, not pen. I'm making mistakes. You're going to make mistakes. It happens. Okay. Again, you got two more kind of along the same lines there. And as always, setting up the equations to me is that tricky part. Going to go through one last problem. So I'm going to flip this over after you've written this all down. And maybe at this one, we'll just set up the equations and I'll let you solve it so we can get you all working. All right. So the last ones are break-even problems, typically related to when some kind of, like a lot of this is kind of business related, so maybe like earnings as opposed to spending and when those things might be equal. So the equations are actually going to look a little bit different than what we had just built. Now, again, we want to start with our variables. So our problem reads that a bike shop costs $2,400 per month just to operate. The store pays an average of $60 per bike. So that's how much they're paying to build the bike, not how much they're earning. And then the average selling price of each bike is $120. How many bikes must the store sell each month to break even? So we're, again, defining our variables based on this last part here. And for sure, one of the variables is going to be the number of bikes. So how many bikes must the store sell each month to break even? So that last sentence doesn't do a great job of giving us two variables there. I definitely see the first one with the bikes, but there's not two different types of bikes, right? It's not like bike number one and bike number two. So then I'm like, okay, what would that second variable might be? Well, the second variable might be, and when I'm looking in this equation, I'm seeing a lot of things related to money. Okay, so something related to money. So y is it the amount they bring in or the amount they spend? Let's say the dollars spent by the store. I think that should work here. We might end up switching that around here in a second. Okay, so the break even is how many bikes and what dollar amount will they get to be the same so that their costs are equal to their spending. So then I'm like, okay, we've got two equations. We've got one, just how much it costs the store to operate, so the $2,400 per month, but then we have to add on how much it costs for them to get the bikes in the store. So these two pieces of information is one of our equation. So equation on spending. Sorry, that looks really messy, but that says spending at the bottom, one equation on spending. And then the other equation is how much the store brings in. So we have a second equation on the earning. Okay, so the first equation related to just their spending, the amount of money they've spent, so y equals the number of bikes times their cost, so 60x. Okay, depending on how many bikes they want to sell, they've got to purchase all those bikes. So $60 times the number of bikes they bring in. And then we have to add on the $2,400 that it costs to operate. That might be like warehouse costs. That might be them paying their employees. It could be a number of different things that they're accounting for in that $2,400. Okay, then the other equation, and again, we've dealt with all of this part, is just how much they bring in, which is 120x. Right, so this equation is them spending, and this is them earning. So I think we should change, and this might happen where you define your variables, and as you build the equations, you're like, that y isn't exactly defined correctly, right? Not both of these y's are showing how much money was spent by the store. So let's just redefine this y variable so it's a little bit more related here. And y in this case should be just money, right? Because we're either earning it or spending it. Does anybody think of a better way to kind of define that? We're good with just money? I think that basically covers everything. Right? So in this case, it's how much money they've spent. In this equation, it's how much money they've earned. So yeah, I think that works. Okay, just money here. Not as specific as some of the others. And this is what I mean by the equations being set up a little bit different, right? Both of these have y equal to each other. So we can use substitution really easily by subbing 120x in for the other y and solving from there. I'm going to let you all go ahead and do that on your own. That one works out fairly nice. Okay, so again, as you work through this lesson today, define your variables, come up with guesses, do your very best to build equations, but I need you to try that first before you just say, hey, can you come help me and check to see if these equations are right? I'm happy to do that as long as you've given me an initial guess. There's an answer key posted on Schoology with work shown. So once you're all the way done, that's when you can go ahead and start checking those. Okay, the rest of the period is yours to get some work done. If you hear your name, come see me.